the PHYS 2212 Lab 3 circuits. So this lab was intended to teach us how capacitors, resistors, and batteries interact with each other when in a DC circuit. We were also going to use multimeters to experimentally determine, real values of resistance, current, and voltage to compare it to ideal models, as well as explain the behavior of ohmic circuits. Here's a preview of results. The right is the initial experimental system. The system is the circuit, and the surroundings are everything else. The two batteries were both 1.5 volts each for a total of 3 volts. We found that I1 equals I2 as expected. The potential across the 47 ohm resistor was minus 0.76 volts. Across 100 ohm resistor it was minus 1.57 volts. And across the wires it was really low at 4 times 10 to the minus 4 volts. We found that the charging time of an RC circuit, which is part 2, was 5 seconds, and the discharging time was about 2.8. So some fundamental principles that will be used here. First is Kirchhoff's voltage law, which says that the sum of voltages around a loop equals 0. Essentially states voltage is a state function. The Kirchhoff current law states that the sum of current in equals the sum of current out, as well as Ohm's law that states that voltage equals current times resistance. So here is the picture of the circuit from part 1. Okay, we found that you can see that the ammeters both read 15.8 milliamps, which is what we expect to see. And we also found that if we switch the connections, the reading became negative. If we turn one of these ammeters to a voltmeter, we found the voltage to read 2.7 volts, and the other ammeter now read 0. Why does this happen? This is because the voltmeter has an extremely high internal resistance, which essentially stops the flow of all current. So we then removed the voltmeter from the circuit and now used it to measure potentials. I won't read all these numbers, but here are the results from that part. We found that the total sum of voltages was around 0.1 volts. Again, per Kirchhoff's voltage law, it should be 0. This is probably because of non-ideality of the system, as well as possibly measuring errors. So when we attached the voltmeter, the ammeter reading didn't change since, as I already talked about, the voltmeter's resistance is so high that no current can really flow through it, so therefore it's not really going to affect the current in the circuit. And here is just some confirmation that our numbers made sense. We found the 47 ohm resistor had about 47 ohms of resistance. Same with the 100 ohm resistor, and that the wires had very little resistance as expected. So now let's talk about part 2. We generated a RC circuit with a capacitor, a resistor, and a light bulb as the load. Same apparatus, 1 farad capacitor, 2 light bulbs. We found that the 2 ohm bulb started out bright and dimmed over time, both as the capacitor charged and discharged. The 2 ohm bulb took about 5 seconds to charge and 2 seconds to discharge. Now, these times should be exactly the same, or about the same. So why were they not? Well, first, it's very difficult to judge when the light bulb is fully off and you can stop timing. And secondly, more of an experimental reason, batteries have an internal resistance. It is not much, but it is also not negligible, and in our ideal model, we don't account for the battery's resistance. So this leads us to our assumptions and sources of error. First, it's challenging to exactly measure voltages with the multimeters. We also assume all conditions to be ideal. For example, the wires have no resistance, the batteries are at a constant voltage of 3 volts, resistors are at exactly their value, etc. And as I already mentioned, it's very hard to accurately determine when the light bulb totally dims and you can stop the timer. Now, let's talk about what if we charge the capacitor with no resistor. Well, no resistance means that the resistance is 0. If R equals 0, then the denominator in this equation becomes 0, which means we're dividing by 0. Okay, this is mathematically undefined, which means this is not possible. If the time constant is small, then this will decay rapidly, which means that a large amount of current will flow almost instantaneously. So if RC is approaching 0, then long story short, it would mean that the current would flow almost immediately, which would charge the capacitor almost immediately. So in reality, we don't have any objects with 0 resistance, so therefore this situation can never occur because R will never be 0. So therefore instant charging can never occur. So the predicted charging time with no resistor would be instant. The real measured time would be greater than 0. That is all. Thank you.